Yes, great. So, hello, everyone, dear colleagues, dear Black Sea Women Nuclear Network. I'm happy to see you at our third session of Black Sea Expert Nuclear Talks. My name is Dr. Valeria Gergieva. I am a research fellow at Odessa Center for Non-Proliferation from Ukraine, but currently I am based in Hamburg as I am visiting fellow at the Institute for Peace Research and Security Policy at the University of Hamburg. Few words about our Black Sea Experts Nuclear Talks initiative, as it is quite a new initiative by Black Sea Women in Nuclear Network. And the main aim is to increase awareness about the most relevant issues, news, recent research, as well as to share ideas and expertise in nuclear fields, non-proliferation, and nuclear security. And today we have quite a relevant topic which is on the agenda now, which calls radiation protection, what we need to know and how not to drown in an oversaturated information space. The issue about this topic is that not a lot of people are aware of the basic of radiation and how to protect themselves. So radiation is everywhere. Living on this planet means being exposed to natural radiation as well. And some of the most familiar sources of radiation include the sun, microwave, ovens in our kitchens, and the radios we listen in our cars. And most of this radiation carries no risk to our health, but some does. And mostly population is not familiar with basic knowledge of radiation, as I said, and look quite suspiciously, especially to such issues like nuclear energy. Also, there is a certain post-Chernobyl and Fukushima syndrome, which cause fear on nuclear energy. So today we will try to answer on the main question and to talk about certain steps, what is radiation, how to protect yourself if there will be any radiation or accidents, etc., etc. So you are welcome to ask questions, to add what you are thinking about it at the end of our speakers' presentations. So firstly, we will listen to all speakers, and then we will have enough time for questions and discussions. I wanted to start with Ms. Yelena Mursa. If Dr. George Moore has time, you will be the second. Ms. Yelena Mursa, unfortunately, is not able to be in person today because she has very important issues in the ministry. It appeared last minute, but she was very kindly to record for us a PowerPoint presentation with audio, and she will tell us the fundamentals of radiations. The presentation will be not very long. I will share it. I hope everyone will hear it well, but I was tested and it was good. So I will share my screen. So share. So if everyone
Good
here,
afternoon to everyone. Today I'll make a brief information into the basis of radiation. Namely, I'll talk about physics of radiation. All the matter in the world is made up of atoms. Each atom contains a tiny central positively charged nucleus and a number of electrons. The electrons carry negatively electric charge and move around the nucleus in shells with loosely defined boundaries. The nucleus of the atom contains protons, which carry positive charge equal to the electrons' negative charge, and neutrons, which carry no charge at all. Atoms normally contain equal number of protons and electrons, and are therefore electrically neutral. The illustration shows the oxygen atom planetary model with a nucleus of 8 protons, 8 neutrons, and 8 orbital electrons. The number of electrons in the atom, and hence the number of protons in the nucleus, called the atomic number, gives an element its unique characteristics. The atomic number of carbon is 6, for instance, whereas for lead is 82. Because protons and neutrons, which have approximately the same mass and are much heavier than electrons, most of the atom's mass is concentrated in the nucleus. The total number of an atom's protons and neutrons is called mass number. Since the number of electrons equals the number of protons in an electrically neutral atom, we can specify an atomic species by the number of protons and neutrons it contains. Moreover, since the number of protons is unique to each element, we can simply use the name of the element together with the mass number to specify each species of nuclide. So, carbon-12 is a nuclide with 6 protons plus 6 neutrons. Lead-2008, for comparison, is a nuclide with 82 protons and 126 neutrons. Nucleus of an element that have the same number of protons but different number of neutrons are called isotopes and elements. Hydrogen, for instance, has 3 isotopes. Hydrogen-1, common hydrogen with a nucleus of only 1 proton. Hydrogen-2, called deuterium, 1 proton and 1 neutron. And hydrogen-3, called tritium, 1 proton and 2 neutrons. Iron has 10 isotopes, from iron 52 to iron 61, all with 26 protons that characterize the element, but with 26 to 35 neutrons. Atoms of the same or different elements can combine to form larger electrically neutral entities called molecules. Atoms combine to form molecules to gain stability and remain in the minimum state of energy. For example, 2 atoms of oxygen from 1 molecule of oxygen and 2 atoms of hydrogen combine with 1 atom of oxygen to form 1 molecule of water. Alpha particles consist of 2 protons and 2 neutrons bound together. They are heavy and have 2 positive charges. The alpha radiation can be absorbed completely by paper or skin. Nuclei with too many neutrons tend to transform themselves into a more stable structure by converting a neutron to a proton. This process, known as beta decay, results in the emission of a negatively charged electron called a beta particle. And beta radiation can be absorbed completely by sheets of plastic, glass or metal. And nuclei with too many protons convert the excess protons to neutrons. This transformation often leaves the nucleus with excess energy that is loses as gamma rays. Gamma radiation can be very penetrating, and only a substantial thickness of dense materials such steel or lead can provide good shielding. Larger stable nuclei have slightly more neutrons than protons. Some nuclei are unstable, meaning that they undergo some internal changes spontaneously. In this process, the nucleus gives off a subatomic particle, a burst of energy above. The act of transformation is termed decay, and the nuclide that changes and emits radiation is called radionuclide. Other naturally occurred radionuclides are formed in sequences of series of decays that originate from the elements uranium and thorium. Each of these series ends with a stable nuclide. The diagram on this slide shows the decay series from uranium-2038 ending in the stable nuclide of lead-2006. An electron in the material may receive enough energy to escape from an atom, leaving the atom or molecule thus formed positively charged. The figure illustrates this process for a molecule of water. The molecule has 10 protons and 10 electrons altogether, but only 9 atomic electrons remain after a charged particle passes by. The molecule as a whole is left with one excess positive charge. The process by which a neutral atom or molecule becomes charged is called ionizing, and the resulting entity is an ion. Once removed from an atom, an electron may in turn ionize other atoms or molecules. Nuclides undergoing spontaneous random disintegration, usually accompanied by the emission of radiation, is called radioactive material. Nuclides capable of sustaining a chain reaction of nuclear fission is called fissile material. These include uranium-2033, plutonium-2039, and fertile material represent nuclides that don't undergo fission, but from which fissile material can be generated by neutron absorption and nuclear conversion. This nuclide can be thorium-2052, uranium-2034, plutonium-2038. And nuclear material is a term for nuclides used in nuclear technology system. During the past few decades, several hundred radioactive isotopes of natural elements have been produced artificially, including, for example, strontium-90, cesium-157, and iodine-151. The heaviest element existing in nature is uranium. However, so-called transuranium elements have been produced by man. In this session, we talk about only a part of basic of radiation, namely about the physics of radiation. Regarding radiation units and measurements, sources of radiation exposure, radiation biology, stochastic and deterministic effects, I hope they will be addressed in a future meeting within the NucTalk initiative.
Okay. Yes, thank you, Miss Elena Murza. She doesn't hear us, but oh, sorry, she doesn't hear us. But it was a great beginning, especially for people from nuclear non-proliferation and policy. It's very good, firstly, to begin with such technical issues. And it's my privilege to announce the second speaker, Dr. George Moore. First of all, thank you for joining us and for your contribution. Dr. George Moore is a scientist in residence at the James Martin Center for Non-Proliferation Studies in Monterey, California. He teaches courses and workshops in nuclear trafficking, nuclear forensics, cybersecurity, drones, and surveillance, and various other legal and technical topics such as weapons testing, the CTBT, and nuclear security. I won't read the whole bio of our speakers, as you will be able to find them on our website. We will share in the messages our website, Twitter, and you can follow us and to read more information about all contributors and members and our future events there. So, Dr. George Moore, the floor is yours, please.
Thank you, Valeria. I would like to share my screen now. You're going to have to make me a co-host probably to allow me to share my screen.
Now it should work, yes?
Yes, it will work now.
Yep,
okay,
great.
Hold on just a minute. Okay, should be seeing my screen. Do you see my screen?
Yes, we see.
Okay, so I'm going to talk to you this morning, well, morning my time, afternoon your time, about dose and detection. It's a follow-on to the talk that you just saw. I'm, as Valeria mentioned, I'm a scientist in residence at Middlebury, Monterey, and this is a topic near and dear to my heart. Okay, so what we'll cover is, what is dose? What does that term mean? We'll talk about how we can detect radioactivity, how you can protect yourself. Even if you're not a radiation worker, just the general public needs to know how to protect themselves. And there are 3 basic ways that you protect yourself: time, distance, and shielding. We'll talk about those. And finally, if we have a few minutes at the end, we'll throw in, how does the international community categorize nuclear and other radioactive materials? Okay, as you just saw, this is the way science views the nucleus, the electrons, etc. Now, let me maybe give you a better view. This is one that a lot of people particularly like. You've got the proton and neutron, and over here, away a bit, you've got the electron. So we talk about radiation. Children know what radiation is. It's what made Spider-Man and gave him his superpowers. What made the Incredible Hulk. All these scary things. My favorite, Godzilla, from the old Japanese Toho movies. Monster created by radiation from nuclear weapons. These are all misapprehensions, but everyone knows something about radiation, even if what they know is basically wrong. So you have to deal with that. So let's talk about dose. It's a way that we measure how much radiation a person receives and how dangerous it is. Before we talk about dose, so we have to talk about how we measure how much radioactivity there is. We talk in terms of curies or becquerels. These are 2 types of measurements that basically tell us if we have a little sample, let's say of cobalt-60 or iridium-192 or any of the radionuclides that are of interest. It tells us how much we have in that sample. And we measure that by looking at how many disintegrations per second we have. So we have this old term, curie, 3.7 times 10 to the 10th disintegrations per second, or 37 gigabecquerel. Becquerel is 1 disintegration per second. That's the new term. It turns out that a lot of us like the old term, the Curie, named for Madame Curie. And the reason we like the old term is because most of the useful things in nature, or I should say in our environment, the sources we handle, things like that, are multiples, one way or the other, of Curies. Where does this strange term come from? 3.7 times 10 to the 10th. It's the number of disintegrations per second in a gram of radium-226. That's what Madame Curie researched. So it's a very kind of natural term. How much is in a gram of radium? The becquerel, the more modern term, the disintegrations per second, when we talk about a gram of radium, then we have to talk about that's 37 gigabecquerel. And things get worse from there. And you start talking about petabecquerel. And who knows what those things are? They're very big numbers, and those are hard to comprehend. So a lot of people work in terms of curies. There's this conversion you can do. If you have a number of curies, let's say I have 10 curies, I divide that by 3.7, or I multiply that by 3.7 times 10 to the 10th, and that tells me how many becquerel I have. Okay, a becquerel source, as you'll see later, is a very, very small source. Okay, so once we know how much radioactivity we have, we can begin to think about how much does a person get from that. In other words, how dangerous is a 1 Curie cobalt-60 source? So dose is what we measure. What we measure it in are some terms called sieverts and rem. Rem stands for Rinkin equivalent man. Sievert is the more modern term. There's a very easy conversion factor for these. 100 rem is equal to 1 sievert. We also talk in terms of quality factors. When we have a 1 Curie source of cobalt-60, it's not the same in terms of dose as having a 1 Curie source of californium-252, which is a neutron emitter. That neutron emitter is 10 to 20 times more dangerous and gives 10 to 20 times more dose to people. So we have sieverts, we have RIM. These are what are effective on our body. They're almost the same as what the energy deposition is. The energy deposition terms are grays or rads. So your body's a big bag of water and hydrocarbons, right? And you know, we're full of vacuum. So we really try to think about how does radiation affect the major components of the body. There's also a term that you should become familiar with. This is what's called an LD50 or lethal dose 50. This is a dose that will kill 50% of the population if they don't receive medical treatment. And that dose is about 3 sieverts or about 300 RIM. So if you've received, you begin to see damage to your chromosomes that can be measured at about 25 RIM. At about 100 RIM, begin to see classic radiation sickness. This is where people get nauseated, they start to throw up, eventually maybe some of their hair falls out, etc. But at 300, you're in serious trouble without severe medical attention. So, and about 50% of the population is going to die if they receive that. That's not a bright line. It's not like, oh, well, 300 is here and 301, you're dead, 299, you're safe. All of this varies from person to person. It can vary by what you had for breakfast the morning of the exposure. Now, that's a strange thing to say, but that's because the lining of your stomach has the fastest growing cells in your body, and those are the ones that are most affected by radiation. So if you have a nice full stomach, you actually have shielded yourself a little bit and protected yourself. So we talk in terms of dose in sieverts or RIM. Those are the measurements we give. These are the kind of effects that you have. This is on the upper left is a woman who was a survivor from Hiroshima. She was wearing a printed dress. The flash, which was essentially light energy, burned the pattern of her dress into her skin because the light area is reflected and the dark area is absorbed. Terrible. These are exposures from incidents where in scrapyards, people have opened radioactive sources. The most famous of those is the one in Goiânia, Brazil. Okay. Burns from radiation. Go back and look at these. These are burns. They look like people have been burned in a fire to some extent, but they're different because radiation burns start deeper in the skin. A fire burn starts on the outside and this damage goes inward. The radiation damage starts the inside. They're very difficult to heal. You have, when you're talking about sources, you have to think about how does the environment, how does nature select some of these radionuclides from Chernobyl. Major component early on was iodine, and iodine is a thyroid seeker, particularly dangerous for small children. So that's bioselectivity. Some fish will apportion radionuclides to different parts of their body. People do the same thing. We also have to think in terms of the biological half-life of these materials. If you ingest a radionuclide, it has its own radioactive half-life, which was mentioned in the previous presentation, but it also has a biological half-life. For example, tritium, the hydrogen with 2 extra neutrons. Tritium has a proton and 2 neutrons. So it has a 12-year half-life, but the half-life in your body is only about 20 some days. So if you drink a glass of tritiated water, half of it's going to be gone. That water is going to be gone out of your body in about 20 days. So you don't get the full dose from all the material that's in the water you drink because part of it has left your body. How do we detect radiation? Well, each one of you can detect radiation, but not the kind of radiation we're worried about. Each one of us detects radiation because this is the electromagnetic spectrum. On the right-hand side at the high energies, we have X-rays, gamma rays, cosmic rays. Remember, the gamma rays are the things we've been talking about. But right here in the center, we have visible light. Visible light is exactly the same type of radiation, only it's lower energy. And our eyes and our brain put together are the greatest radiation detector in the world. If we could build a radiation detector for gamma rays or X-rays that was even a fraction as good as your eyes, we would be in great shape. Now, somewhere down here, somewhere in this, usually right about here between UV, above UV, we go from non-ionizing radiation to ionizing radiation. Remember, the previous speaker talked about how you create ions. Well, ions are very dangerous because they are much more chemically active. So their chemical activity makes them bad for your body. You don't want your DNA changing its chemistry. You don't want major components cross-linking hydrogen bonds, doing things like that. So down here in radio frequency and microwaves, we're kind of okay. Up here, we're in big trouble. You got to protect yourself. So we can't detect anything other than the visible light. We can't detect these X-rays and we can't detect these gamma rays. So we have to rely on some sort of detector to convert those radiations, both particle and electromagnetic, particle being the neutrons, alpha particles, beta particles, to something that we can actually use, some signal that we can process, some meter that we can read. And alphas and neutrons usually require a special detector. The most common detector, which works with betas and gammas, is something simple like a Geiger counter. We also have a whole spectrum of things. If you've been involved with borders or any place where they're checking for radiation, you've probably seen radiation portals. These can be very huge. In the Russian Federation, they have some that even work for trains, but they're vehicle, pedestrian, etc. Then there are handhelds. This RID, as a radioisotope identifier, is very special because it can actually tell you what kind of radiation is involved. A simple Geiger counter only tells you that there is some sort of radiation, that there's some sort of maybe dose that you're receiving at that point in space. So here are some examples. Here's on the left, a Geiger counter. This has what we call a pancake head on it. On the right, this is a high purity germanium system. The scale on this is about maybe 3 feet tall. It's a big thing, and this big bulky thing down here is a liquid nitrogen dewar. That's a liquid nitrogen thermos. Here is a more sophisticated thing. This is a portable refrigeration unit. This refrigeration unit will go down to liquid nitrogen temperatures, which you need for the high purity germanium. This, you can carry it around, weighs about 20 pounds. It's called the Ortec Detective. Several manufacturers make things like this now. So we can get, in the old days, you had to come to a laboratory because this thing is big and bulky and liquid nitrogen is difficult to carry around. Now you can go out in the field and get the same quality of analysis in the field. These are some personal items that you might wear. Thermal TLDs. This is a finger ring. You actually put it on your finger when you're handling things with your hands. The downside, this is the detection side, that's towards your palm. But all of these will give you a readout in long term. These do not give you a direct readout right now of what you get, but they give you the integrated dose over time. This is a radiation pager, has a little LED detector. This gives you a real-time readout. And the old gold leaf dosimeters could give you a real-time readout of what kind of radiation field you are in and what kind of dose you might be getting. So neutron detection, I don't want to spend any time on this. As a kind of an esoteric topic, but just understand that neutron detection is a difficult thing to do. First of all, there aren't many neutron sources out there to detect. This is a neutron detector, has a big plastic ball or a big plastic cylinder because we want to slow the neutrons down in order to detect them. Another term that you're going to hear something about is NORM. This is naturally occurring radioactive material. Where do these naturally occurring radioactive materials come from? Some have been around forever. By forever, I mean since the world began. Some are created in real time. So how many of you are radioactive? That's kind of hard to ask for a show of hands. The answer is all of us are radioactive. All of us have radioactive materials in us. And there are two types. The type from the world began, it's like, uranium, as was pointed out, uranium, it showed a decay chart, both uranium-238, 235, 234, they're radioactive. The 235 and the 238 have been here since the world was formed, maybe 4.5 billion years ago. I don't want to, some people have religious beliefs that make that much shorter, but generally science agrees the Earth is about 4.5 billion years old. The universe is about 14 billion years old. So our Earth is a fairly, newcomer. There was a famous astrophysicist in the United States, Carl Sagan, did a program called NOVA. You may have seen NOVA. It was produced all over the world, a science program, education program. And I think one of his great sayings is he used to say, "We are the stuff made of stars." And it's really true. The Earth was formed from the residue of earlier stars that had lived through their life cycle, exploded, sent their contents out into the universe, it coalesced into the Earth. We have these things that are there from the very beginning. Then we have things that are induced now. And induced now, we have cosmic rays in the upper atmosphere. In particular, we get a production of carbon-14. So we have one of the major things that we have in our body is potassium-40. That's been here forever. Carbon-14 is something that's produced in real time. And this is the basis of carbon dating, which you may have heard of. Things that breathe have a constant ratio. We're breathing carbon. Our bodies, if you took a little chunk out of our body and examined the carbon, it would consist of carbon-12, which is stable carbon, and it would consist of a little bit of carbon-14, which is radioactive. When we die, or when a plant dies, because plants breathe, trees, things like that, when we die, we stop breathing, so that carbon begins to decay away, and we can actually measure how old something is by looking at the carbon-14 to carbon-12 ratio, or looking at the carbon-12 to carbon-14 ratio. Norm is a problem for detection systems. When you put a portal out in the field and people start walking through it, you would like it to be, well, we can just, any radiation that the portal detects is bad, right? Well, the problem is the portal's sitting in a norm field, and that norm field changes. Like if the portal is set out in a place where it snows, the amount of norm that it detects will change as a function of time. So it's a real problem. Interesting fact, this is actually inaccurate. This is an older slide. A banana contains about 15 becquerel of potassium-40. So a big truck trailer full of bananas can actually set off a radiation detector. So if you like it, you can calculate how much a dose you get from potassium in your body. You can figure out how much dose you get from bananas you eat. Bananas are not unique. Kiwi fruit, lots of other things also have radioactive materials in them. Okay, this is the last, well, not the last thing. This is a thing that I want everybody to understand, which is the difference between exposure and contamination. Okay. If you're at home like me and you have a coffee cup, or you're in the conference room and you have a coffee cup, imagine your coffee cup is full of some sort of radioactive liquid. Now, you would be getting a dose from that radiation coming through the walls of the coffee cup, coming into your body. But there's no contamination until you do something like spill your coffee or have a sip. Now I have contamination on my mouth. I have internal contamination. I will then have internal exposure from the internal contamination. As long as I keep it out here, I have external exposure. And for some types of radiation, that is absolutely critical. Alpha particle radiation will not penetrate the outer layers of your skin. But if you get it inside you, like Mr. Litvinenko did in the UK, and other people have gotten through inhalation accidents, you're in big trouble. It can kill you because it's now exposed to the fresh cells in your lungs and fresh cells in your organs. And the alpha particle is just like a freight train when it hits a cell. It kills cells. Gamma rays, for the most part, kind of go right through. It's a very chancy thing. As you sit here or wherever you're sitting, you're probably being struck 5,000 to 6,000 times per second by gamma rays. That sounds really, really weird, but it's true. Okay, so difference between that. Protection, time, distance, and shielding. Shielding is a matter for experts. Alpha particle will be stopped by paper, the dead layer of skin on the outer side of your body. Beta particles will go through, you need some sort of light aluminum. Plastic, if it's thick enough, might stop them. Gamma rays or X-rays, you got to have something like lead to really absorb them. One of the things that I see people telling first responders, which is wrong, is that your clothing, your response clothing, will protect you against beta particles. It will give some protection, so would a sheet of paper, but you really need, if you wear an aluminum suit that's about a half-inch thick, maybe that would be okay, like a suit of armor, like a knight made out of aluminum. But your regular stuff is not going to give you protection. So you have shielding. Here is a picture. This is an exercise that was held a number of years ago in the old Vienna airport. Some of you may recognize the Vienna airport baggage area. This is a guy in an old style bomb suit with an Ortec detective, and he's opening what could be a bomb package. This is a very, very bad example of how to do things. But you're seeing here some things. Going back here, time. Time is linear. The longer you're around a source at a particular distance, the more dose you're going to receive. That's linear. If you're there for a minute and you're there for 60 minutes, when you're there for 60 minutes, you receive 60 times the dose that you receive when you're there for a minute. Distance is a big factor. Distance goes as a square of the distance. So if you're at a foot and you move back to 3 feet, you drop the dose by 1/9 by the square of that distance. If you drop back to 10 feet, you've dropped the dose to 1/100th of what it is at a foot. So for first responders, we always tell them, don't stay around a radiation source. Get away, minimize your time. Shielding is for experts. Okay. Categorization, real quickly. This is the way the IAEA categorizes radiation sources in 5 categories, starting from the most dangerous being 1 to the least dangerous being 5. This shows up in RSG 1.8. It's a guide for the 80, and each radionuclide has what's called a D value. Some people call that a danger value. You take how much activity you have in either Curies or becquerels. The tables allow you to use either entry. You calculate the A over D ratio, which is a simple number, and then it tells you what category this falls into. This is an example from RSG 1.8. Here's another example of the same table. This is how you categorize nuclear material, plutonium, uranium, etc. You categorize by how much you have based on the weight of the material. All this nuclear material, the stuff you can make bombs out of, is radioactive, but it's very slightly radioactive. Okay, I'll leave this for you. This is, I'll give Valeria a copy of this presentation. A day without radiation is a day without sunshine. And there are various things. This is in the United States. This is the average annual dose that people receive from background radiation and from all other sources, about 350, 300, 400 millirims per year. And you can calculate that if you want to convert it into sieverts. But you see that the man-made portion the medical x-rays, nuclear medicine, consumer products, things that are radioactive, stuff you eat in the food, is a small fraction of the overall. And this can vary tremendously by where you live in terms of the radon exposure. Okay, that's all I wanted to say. And thank you very much for paying attention. There are some questions in the chat box.
Yes, thank you, Dr. Moore. It was very comprehensive presentation. I'm sure that we have some questions, and as I know that you need to go quite soon in 10 minutes, I will ask our participants to ask questions to Dr. Moore now. So please, do we have any questions? Yes, I see Ali Alkish, the first question. Yes, please.
Thank you, Dr. Moore, for the informative presentation. I really enjoyed it while listening. You mentioned about exposure and contamination, and you made clear the differences. But I would like to learn what should we do and how can we protect ourselves and how can we limit contamination? Let's say we have been to a place that there was some kind of radiation leak, or there was some kind of dirty bomb, but we didn't affect it, but we have been to that area. So how can we limit contamination individually?
Well, it's pretty hard to do it individually. It's usually not done that way. I used to run, we call it a decontamination line. If, for example, if there were a dirty bomb, the authorities, the first responders should come and they should set up, block off the area around that. And anybody coming out of that area needs to be monitored and checked to see if they have contamination. Then you remove their clothing. You may discard their clothing. You would shower them down, hose them off, however you can do it, scrub them down with soap, water to try and make sure that you can remove any external contamination. Then you might take the next step, which is actually send them for whole body counting to see if they have absorbed, if they've taken anything internally. That's a very complicated, the whole body counting is a very complicated process. But if you look at there's an IAEA report on the Goiânia accident, you'll see that the Brazilian Radiation Authority, in fact, you'll see a picture of my old colleague, Carlos Nogueira, with a made up body scanner. They made up a body scanner, just created one that they could use to give quick ideas of whether people had internal contamination or not as a screening method. They had to screen over 100,000 people for contamination and exposure. So yourself, you wouldn't know if you're contaminated or not. I mean, you might know if you were around something. It's kind of a, when we talk about weapons effects, nuclear weapons effects, a lot of people have the idea that if there's fallout, it's invisible. Serious fallout is not invisible. Serious fallout looks like snowfall. It's flakes of material. So then you would know, I mean, if your stuff is sticking on you, falling out of the sky, you know to get it off of you. A common practice, for example, when you're around any kind of radioactive material, is no eating, drinking, or smoking around those, because those are all internal pathways that you could have into your body. You want to make sure that you always have things on the outside. One of the things, I hadn't really thought about this, most of us during COVID have been wearing facial masks. I mean, these are not respirators like we would wear in a laboratory, but they would afford you some protection if you were in a situation where there was any airborne activity, because that airborne activity is going to have some size, and the mask may protect you to some extent. If you have an FFP2 mask or a KN95 mask, they're designed to trap virus size particles. So some things would probably get through, but a lot of stuff would probably be residual on the mask, and you throw the mask away.
Thank you so much.
I'm not sure. Other questions?
Thank you, Ali. Dear participants, if you ask questions, please introduce yourself firstly. So do we have any other questions from the audience? Because I have one question to Dr. Moore as well, if I may. So I have already introduced myself, so no need. So Dr. Moore, is there a difference between radiation in case of nuclear warhead explosion and accident at the nuclear power plant? And if there is this difference, what people should do to protect themselves in any case of these scenarios? Yes, thank you.
There are some, I'll call them subtle differences. The nuclear weapon will have either be a fission-only device or have a fission trigger. There'll be a slightly different distribution of fission fragments, but as a first-order approximation, they're going to be the same. One of the things that can be done, because you can anticipate a reactor accident, maybe, I shouldn't say anticipate like you think one's going to happen at any time. Remember we talked about iodine going to the thyroid. You can actually take potassium tablets and potassium iodide and block. You load the thyroid up with stable material so that the radioactive material won't get into the thyroid. So there are some things you can do. For nuclear weapons, they could be anywhere. But we have looked at in the United States, and maybe in some places, I think, they've actually made available to the general public who live around nuclear power plants these types of blockers that people could take in the event that there was an accident. It's kind of hard to go around and pass them out after the accident occurs. So you want people to have them before any accident occurs. And there's pros and cons to that argument. And there's, people say if you pass these out, it just excites the public, and they're worried, and some people might take them. They're not risk-free themselves. Protecting children is maybe a reasonable thing to do, but they're more risky with children. There looks like there's another question from Dan.
Yes, please, Dan Fenstermacher. Please introduce yourself.
Yes, hello, I'm Dan Fenstermacher. I'm a physicist with the Department of State in the Nuclear Energy Safety and Security Office, and I've long had a project to help the public, to do something to help communication with the public about radiation. And all these units, RADs, REMs, Grays, Sieverts, Becquerels, as you said, they're very confusing. So what I've been talking up in both the G7 context, the Nuclear Safety and Security Group, and also presented once to the National Academies, is for purpose of reporting and policymakers to adopt a relative unit, just a normalized unit. And I call it the RAD-RISC, Radiation Richter Scale, RI for Richter and SC for scale. And it's just a normalized logarithmical scale based on what I think we should adopt as a background unit. And you said 355 millirems per year. That's just about exactly 10 microsieverts per day. So that's kind of what I would propose we adopt globally as a background, sort of like a salt intake, right? You don't want too much salt, but the normal salt intake is so many micrograms per day, or sugar, some of the things that are bad for you in large doses. There's a normal thing, there's a normal background. And so I proposed this scale where it's then logarithmic based on that. So everything instead of sieverts, when we have exposures, would be in terms of, when we have radiation fields, in terms of this RAD-RISC logarithmic scale, where 0 is nothing. And it very nicely correlates with earthquakes. When you get up to 10 to the 9th, like a magnitude 8 or 9 earthquake, it's devastating. It's well past the LD50 if you're there for just a small amount of time. But in the RAD-RISC 2-3 scale, just like earthquakes that just rumble a little bit our buildings. So I've talked this up, and I'd love to collaborate with any of you on this idea because I think it would be very helpful. Then when we would report radiation doses, we'd simply do it in terms of number of days or weeks or months of background. So not the total dose that we receive in terms of these units, whether they're rads or REMs or right, but just in terms of time. So a dental X-ray is 10 extra days of background. A flight across the country is a few extra days of background. If we're in a nuclear accident region and a rad worker, we might receive an extra year of background in a severe accident. The rad workers at Fukushima's, and you can translate everything into just a simple number of extra days or time of background, and then this rad risk scale. I find it very compelling, at least as a physicist who's worked in 30 years in the policy realm, and so I just wanted to throw it out there.
I think that's a very interesting idea. Be glad to talk to you about it. If there aren't any other questions.
Yes, we have questions from Shabnam Odoom. Please, is your connection better?
Hello, good morning and good evening to us. Can you hear me well?
Yes, I can hear you.
My name is Shabnam Odoom, and I'm a professor of international relations at Hacettepe University in Turkey, in Ankara. And my question is, looking to a scenario of a possible attack with this radioactive material, how much of them would a perpetrator would want to obtain to affect humans with radiation and cause damage?
Well, I mean, I don't know that there's a specific. We could talk about a whole spectrum of things. What we're really then talking about is radioactive dispersal devices or radiological dispersal devices. There are different types. The one that gets the most publicity is what's called a dirty bomb, where you take some material and pack some explosive around it and try and set that off to spread the radiation. Maybe not the best way of actually, or the most effective way of using the radiation. So you'll find that hospitals, blood centers, things like that, contain sometimes fairly large radiation sources. So their security is important. It depends on the type of material that's stolen. It depends on, we have probably on the order of 5 to 10 million legal shipments of radioactive material, primarily medical isotopes or medical radionuclides, every year. The medical radionuclides are usually a lot less dangerous because they have very short half-lives. So because you don't want, when you put something in somebody's body, you don't want it to stay there for a long time unless you intend it to be that way. And there are some cancer treatments where you do implant brachytherapy sources into the body, particularly like for treating male prostate cancer. So there's no if you look at that categorization scale from the IAEA, it's RSG 1.8 or 1.9. I'm blocking right now. I'm remembering which one it is. If you look at that scale, the level 3 and above are the ones that are really particularly dangerous to people. Level 4, category 4, is also dangerous, but in a longer term. So the ones in any category 3 or above source, which is stolen or out of control, potentially presents a hazard if people want to use it maliciously.
Thank
so
you.
I guess that would be the guideline: is look at what the nuclide is, look at how much you have to make a category 3 source, and then that would be kind of a working threshold for what's really considered to be dangerous. But there are a lot of these things around in places you don't think about. For example, the whole blood industry radiates blood to prevent host versus graft disease. This is a disease, particularly in more homogeneous cultures like in Japan. It's a 100% deadly disease if you get it, and it can be prevented by radioactively sterilizing the blood. And these blood irradiators are big sources. We do the same thing. We also do food sources. Back in the old days of the Soviet Union, they actually had big cesium-137 sources that went out into the field while they were picking corn, potatoes, etc. They threw the corn and potatoes into a hopper, and it ran through this big radiation source and sterilized it right on site. The scary thing is nobody's real sure where all of those trucks and all those sources went. The Chinese did the same thing. In the Soviet system, those were called, I think, kolos, if I'm recalling correctly, which is like ear of corn. I'm probably mispronouncing it, but these were big truck-mounted sources.
Thank you. Thank you very much.
Thank you. Thank you very much. Can I ask for one small issue? Can participants who are able to turn their cameras, because I want to make a screenshot of our meeting, and if it is possible for you, I will be very glad. Oh, thank you. Thank you. Oh, great. Everyone is here. Okay. Okay, 1, 2, 3. Great. Thank you very much. Are there any more questions to Dr. Moore? Because as I know, he needs to go already. If no, I want to thank Dr. Moore one more time for joining us. It was a very comprehensive speech, caused a lot of questions of everyone, and I'm sure there will be more questions. So thank you very much. As a person from non-proliferation, I don't know anything about the radiation, but now I feel myself like not an expert, of course, but I feel more confidence in these issues. Thank you very much for your time. So, and we have, oh, yes, please.
No, I was just waving goodbye.
Oh, yeah. Goodbye. Thank you one more time. But we are staying here because we have one more presentation, which is also very important and will be interesting to hear about. It will be by Dr. Lia Chelidze. She is a TCU Andronikashvili Institute of Physics. She is president-elected of Georgian Health Physics chapter and member of Commission of Nuclear Energy and Radiation Safety of National Academy of Science of Georgia. You will be able also to look at her full bio at our website. So please follow our website and our Twitter, etc., etc. As I know, Ali already sent our links in the chat. So Dr. Lia Chelidze, please, the floor is yours. She will, sorry, I forgot to tell, she will talk about reliable sources of knowledge about radiation. So please.
Thank you. So I appreciate this opportunity to take part and speak with my colleagues. And yes, we speak about reliable source of knowledge about the radiation. The most short answer is reliable institutions are the reliable source of information related radiation. And a little introduction. Throughout the history of its existence, mankind has been exposed to natural radiation, and small amounts of radioactive materials can be found in our bodies, in products we use daily, and so on, in outer space. And they are a natural part of our everyday life, but we cannot say definitely that this radiation was beneficial or harmful to man as a species. Unlike artificial sources, which we have known for only about 100 years, and despite the good received from their use, it has been realized that the radiation from the sources is also harmful. Yes, radiation has no odor or properties that allows it to be seen, and it became clear necessity for the development of a system to protect a person from excessive or unreasonable exposure. And this system has been improved as the effects of ionizing radiation have been studied. Because at the beginning of 20th century, the features of the physical and biological action of X-rays and radium rays were not known. Matter of concern to the physicists of the early 20th century was an urgent need for a population protection aftermath of the atomic bombing. And in 2022, the spectrum of nuclear weapons use has returned to the center stage of Europe. And our purpose is highlight the importance of radiation protection knowledge for population. On the other hand, it is impossible to protect people from hazard if they know nothing about that. It is no less important to give a systematic character to raising the awareness of the population, and population should know the types of radiation, radiation protection, and at what level of radiation is harmful, risks and benefits. Yes, the most easy accessible source of information for the population are special booklets and websites. Web addresses were changed quite rapidly, and the information is sometimes also adapted to specific risks of each country. The internationally recognized reliable sources. Of course, I begin with the International Atomic Energy Agency website, US Environmental Protection Agency, Health Physics Society. For Georgia, for example, we have regulatory body site, and as well we have Non-Proliferation JADE. The site was designed by the Civil Council on Defense and Security, with support from Swedish Radiation and Safety Authority. And it is very important to have such web links and sites. Very good book is for population is basic knowledge of nuclear hazards, lessons from Chernobyl and Fukushima by Viktor Poyarkov, was issued by the European and Mediterranean Major Hazards Agreement Council of Europe. And we speak about professional sites. We all have questions about radiation, and it is not easy to sort through the available material to find answers. Sometimes the information is too technical, or it is too hard to find just the answer you are looking for. Then a professional should explain it to an ordinary person in understandable language. And for clarity, I would like to address the following question. Question 1, if a nuclear accident occurs, what should you do? And the answer is listen to a warning that will be presented through a range of media, TV, radio, or emergency communication. Listen carefully for instructions to learn what protection measures should be implemented. You know that in order to protect the body from external exposure, the following protection measures can be recommended. Protection by distance, going as far as possible from the source of radiation, protection by time, protection by sheltering, in order to protect the body from internal exposure. The following protection measures could be recommended: preventing radionuclides inhalation with masks or wet handkerchief, do not drink water, preventing radionuclides injection, iodine prophylaxis, take stable iodine following the instructions. one question as well. If you are asked to take shelter indoors, what should you do? And the answer is you must go to the nearest available building, house, public facility, etc. Shut all doors and windows, take a shower, wash your hands, stop ventilation fans, put food into containers and wrap it, secure drinking water in sealed container, and so on. So it is very important to have your own knowledge to understand the risk as well, and to understand the recommendation. So it needs some basic knowledge. The one problem which is necessary to discuss with the public, it is general public perception of the radiation safety in normal conditions. Population should know that the limit value for the effective dose aimed at protecting members of the public is 1 millisievert in a calendar year. Every person has the right to protection from influence of ionizing irradiation, and this right is guaranteed if country establish the system of public education and awareness, instructions for iodine prophylaxis and other protective measures, and potentially affected public should be provided with general information about possible nuclear accidents, and this should include the nature and extent of nuclear risks and potential effects on human health, the environment, including property. Unfortunately, recommendation of responding to nuclear emergencies in the form of frequently asked questions sometimes did not work, because to correctly understand answers to some important questions, one should have some basic knowledge. And there is only one way to provide people with trustworthy information about nuclear hazard. This is to give people knowledge about nuclear radiological hazard, allow them to build their own capability for risk assessment. And it's all what I want to say. Thank you.
Yes, thank you very much, Dr. Leah. It was very interesting, and I have some questions, of course, or just comments, I don't know. But firstly, of course, I will ask, do the audience have some questions? Yes, Ali, please.
Thank you for the presentation. It was again very informative. As you mentioned, we should follow the instruction for the government or the agencies, but do you think we should have some kind of medical things with us beforehand in order to be prepared for the radiation emergency, or should we have some kind of potassium iodide or any medical things in our house just in case, as we need to prepare ourselves for any possible radiation emergency?
Some experts recommended to have survive kit. Yes, with light, with mobile, with yes, with some necessary things if you if happens such a disaster, to survive for some days. But people should know that iodine prophylactic work when you take it on time. And it is dosage, and it can be harmful if you take it when you should not take it. So anyways, these recommendations from government and people who understand what they said, because you need some knowledge to understand the recommendations. Why should you receive the iodine prophylaxis? After 3 days, for example, when there is not iodine schlafe, you should not receive this. So everything has his rules.
So we should closely follow what our government says. So instead of doing some proactive things. Thank you.
Yes, sure.
Yes, this is a case which I also faced. Oh, sorry, we have a question. Yes, Margarita.
Valeria, you could finish your comment. I could wait.
Yeah, thank you. Yes, this is the case also I want about these iodine pills. I experienced it maybe several months ago because my even friends and relatives, they of course don't know a lot about radiation, about nuclear energy, etc. And they were panicking a lot. There were no announcements, but there were some news from internet, and people started to buy these tablets and to take them. And the dose, it's very big, so it's very harmful for their body, human, if there is no risk. Of course, if there is radiation, it will help you to protect yourself, but if not, it harms you. And some people don't even read properly, and they started to do it every day. So, and it was a case because I know these people, and this is the case of the importance of about you said to increase awareness, yet of just among the people, to educate them about these issues at school, at the university, and then maybe some courses when you are going to work. I don't know. They should be, because people really harm themselves when they're panicking. So this is very important issue. Yes, please, Margarita, the floor is yours.
Thank you, Valeria, and I think you touched upon what I was going to say. And Dr. Chilidze, thank you so much for your presentation, for your remarks. What you mentioned was that you work with Tamara's organization, I see Tamara online, with the Civil Defense Security in promoting the knowledge about radiation. And I think it's very important because from some governments you hear that, yes, if we talk about radiation, people will start freaking out, that, there's a strong level of phobia. How do we counter that phobia through education, through the partnerships between government and civil society, for example? But I have a question specifically for, maybe in Georgia, do they teach civil defense at high schools, for example? Because as we grew up in the Cold War, in Soviet and American schools, there were civil defense classes where we were told what to do in the case of nuclear explosion. Unfortunately, this knowledge has become very important in the light of the war in Ukraine. So, and I wonder if this is something that you could comment, whether such classes should be taught from the schools and universities to create a better understanding and the self-defense mechanisms of what to do in case of this happening. Thank you.
Thank you. It is very important question. No, it is not in general. People not teach defense. For example, students who has courses on radiation safety, of course, they cover these questions, but it is not for all students in general. So it should be in every school, in every high school teach, but not in not now. It considered. During some years we speak about it, but in some schools, some pilot projects work. And students really need it.
Mm-hmm. Thank you. Thank you. We have two more questions. So the first one from Bahire Gül Göktepe. Are you here? Microphone, please. Micro.
Yes. Again. Hello and good evening to everyone, and greetings from Istanbul, Turkey. I'm very pleased to be in this session because last week During 2nd and 4th December in Ankara, we have an international radiation protection conference. It was really great. We almost covered all the different aspects of radiation protection. So I still feel excited and fresh about all the issues. Thank you to Leah. It was a very interesting talk. If there's a nuclear or radiological emergency, one of the major issues is communication and communicating with public. We'll have to be prepared for this. And I think about 4 years ago, International Atomic Energy Agency held a big conference, which lasted for a whole week. It was the communication after radiological and nuclear emergencies. And I am voluntarily presenting Women in Nuclear Turkey. And we have developed a communication project, how we can inform public in the case of emergency. Mainly politicians do it, and everything may go wrong. No matter how the governments and nuclear communities or nuclear authorities are prepared for radiation protection and they have emergency plans. We know that each country have emergency plans, but the main issue is how it works during the emergency, how they communicate with public, how they use media. And what we learned during various meetings and cases, experts in this field should act so promptly, within minutes, within hours. Otherwise, those who don't know these fields very well, who are not really knowledgeable, they may give wrong messages and everything can go wrong. So this is a very important issue, communication with public. We'll have to be prepared for it, and it is the task of nuclear expert, really. Yes. I just wanted to comment on this. Thank you.
Thank you very much for this comment. I guess we all agree in these issues. We have one more question, and after this question, I will also maybe have a proposal for you. Please, Elizaveta.
Hi, everybody. I hope you can hear me well now. And first, I would like to thank the experts and the moderator of today's session. So I have quite a follow-up to what Margarita and Valeria were mentioning about the education of the children. And so basically, while speaking to some of the like Japanese students, they say that they have from the early childhoods, they have some educational process. So my question is, from which age do you think it's appropriate to start talking to kids in schools or whatever about radiation? Thank you.
It's question to me or it's comment?
It's a question. From which age do you think it's good to start the education process for children at school, for example?
Yes, I like very much US EPA web link radiation for kids. I think from what age? From in school, from the very first classes, people should have some idea. But what is atom, for example? That if radio and I know for sure that in high classes and at high school should be taught more serious detail knowledge should be given to students how to behavior during emergency situation. Because sometimes hazard radiation is hazard itself, but sometimes not knowledge is more hazard. because in Georgia, unfortunately, we have case when people, but it 20 years before, people find lost source in the wood and hit it, and it has fatal, and it has radiation signs. It is a Lilo case, and the International Atomic Energy Agency published this book about Lilo case is one case, and Leah, in village Leah it happened. When people harmful themselves because they have not knowledge about radiation science, about effects, and it is very important because it is live, cannot be everything be prognosis, and it is very important knowledge for every person.
Yes, thank you, Leah. Yeah, today when I was listening to presentations, I remembered my school years, my physics lessons, and I realized that I had lessons exactly about this, but there was no information about how to protect yourself in case of radiation. So we received at school some information, and it's very easy just to add to this maybe physics part, yeah, the block, how to deal with it. Yeah, so maybe since 7th grade, when children are already ready for such kind of information, it will be very useful. But of course, it should be discussable on the Ministry of Education level to include such important parts. So we should discuss it. It's very important discussion, I think, because such discussions can save a lot of lives in case, as you said, Leah, yes, life is unpredictable, and unfortunately the situations as well. Yes, sorry, Bahira Göktepe, do you have a comment? One more comment?
Yes.
Please.
I have a comment. I think we need to teach children in schools about radiation protection? Maybe complicated, but we can definitely teach them how to recognize radiation danger sign. It's very important, because mainly radiation accidents in many countries, like Leah just mentioned, hotspots, what has happened, is due to abundant radioactive sources or medical sources or orphan sources. And and usually there are some signs when these sources are left in the scrap yards or anywhere, or by the leftover by the illicit trafficking or whatever it is. If people could recognize the danger sign, they may immediately report to authorities and things can be done. We had a case, very interesting case, in several years ago in Istanbul, where there was an abundant source in scrap yard, and the family of scrap workers get radiated, and they were getting ill. It's a very interesting story. It became a book. I was one of the authors in public concern section. And how it discovered, it is the care or the knowledge of a medical doctor. He's got suspicions that these family, various people were showing the signs of radiation sickness, and he immediately called the Nuclear Research Center, and then it was the minutes of operation. Usually authorities would know how to act, how to protect the people. If we can identify what happens, if we can identify the incident, radiation incident happened, then it is easier. I remember in that story when this family were trying to get the source from a big container, lead container, there was a sign. Some people recognized and they said that it was dangerous. It's very important, like the no entrance sign, traffic signs. We can teach children among these danger signs, radiation sign. Also, in many schools in our countries, there are emergency practices concerning earthquake. and fire. In addition to this, radiation incidents can be added by the authorities as well. This is, one of my recommendations. Thank you.
Thank you. Thank you. I have a question also for you. You mentioned about the conference in Istanbul about radiation protection. Will be there any more conferences like this?
There will be, because in Turkey it's a very active NGO, Radiation Protection Association. Every 2 or 3 years they hold these conferences, and I'm sure they will organize another one within 2 years. This conference was delayed due to COVID, but it was very good, very international conference. It was 3 years, 3 days. It covered all the main issues and all the updated information and regulations and dosimetry, medical application, nuclear power plant under construction in our country, in the world, and it was very, very interesting aspects of the radiation protection was covered.
Great. Is
Next
it possible?
time we will let you know.
Yes, maybe to exchange our contacts with you, because we have a lot of students who are interested in such topics, to increase also the students' education. So yeah, if it's possible to send us some links.
Yes, Şebnem Udum was one of the speakers. She is also involved in this society.
Great, great. Yes, thank you very much, because we should think about the future cooperation as well. Yeah. If there are no comments more and questions, because we are a little bit out of time, then I want to thank you, first of all, the speakers. Some of them already left. It was really a great talk with the real professionals. Thank you very much. Thank you for the great questions. It was a really comprehensive discussion. We are very fortunate it was recorded, because we can educate more people through our YouTube channel, etc. So thank you. Yeah, I see. Yeah, thank you very much one more time. It was a pleasure to spend this Thursday evening with you. So, and please connect, sign to our Twitter. We will post news of other nuclear talks, also about the relevant topics in the future. And also we have some interesting events, initiatives. Our members are very active professionals, and please join our network as well. Dr. Lia Chelitsa has already joined it. She's our new member. So please feel free to advertise us and to join us. Yes, thank you.
Thank you.